So now I want to go through the process of doing a proof that involves sets because they all kind of follow the same logic to them, which is that we want to basically take an arbitrary element out of one set and shows that it's in another set. So we'll do this just by going through a few proofs. So we'll start with an easy one here, which says that if A is a subset of B and B is a subset of C, then A is a subset of C. Okay. So again, this might seem obvious, but it's really important to actually prove things because sometimes things are, they seem obvious, but they're not. So let's go ahead and see how we would actually go through the proof here. How do we actually show that this is definitely true? Okay, so we want to start with our hypothesis, right? That A is in B and B is in C. So what we can do is we can say, okay, so take X in A. Okay, so in other words, take some arbitrary element out of A. Okay, so we want to start with some arbitrary element in A. Since A is in B, X is in B, right, by the definition. Now, since B is in C, X is in C. Okay. Thus, for any X in A, X is in C. So therefore, A is in C, because that's what the definition is, right? That you can take any element of A and it's going to be in C. So, kind of a basic one, but this kind of shows the process of how these different set proofs will work, is that you find some arbitrary element in the first set and then show that it exists in the second set. So let's go through a bit of a longer one here. Not necessarily harder, but longer. Okay. So this is one we already saw, De Morgan's laws. So let's look at how we would show one of De Morgan's laws. Namely, let's take A intersect B complement is equal to A complement union B complement. Okay. And maybe the other De Morgan's laws I'll leave as like a homework assignment or something, because the process will be pretty similar. Not exactly the same, but similar. So there's two things we need to show. We need to show inclusion in both directions here. Okay, because now we're proving that two sets are equal, not that one's included in the other. So we need to show that this one is included in this one, and this one is included in this one. And when I say included in, I mean a subset of. So we'll divide it into parts here. So part one, we want to show that A intersect B complement is in A complement union B complement. So again, we want to take, I'll do it in a different color here. We want to take some element in the first set and show that it's in the second set. So we want to take X in A intersect B complement. Now, of course, we can't use De Morgan's laws to prove De Morgan's laws, so we can't use this relationship in any form. Okay, so let's just say so X is not in A intersect B, right? So this means either X is not in A or X is not in B, or both, right? So we're using the inclusive or here. So we have two kind of cases here, right? So if X is not in A, then X is in a complement. Okay, this gives us something to work with because we're looking at the complement right now. And then this directly implies, so let's say since X is in a complement, X must be in a complement union B complement, because it just has to be in one of them, and we showed that it's in one of them, right? Now we can do the same thing for the other one. If X is not in B, then X is in B complement, which implies X is in A complement union B complement, right? And if it's not in both, then you can do the same thing for both. Okay. So here we've conclusively shown that if we take any X in A intersect B complement, it has to be in the union of A complement and B complement. So we have proven this direction. Okay. So now we go ahead and do the other direction. So part 2, we want to show A complement union B complement is in A intersect B complement. Okay, so now we need to take some arbitrary element out of this one and show that it ends up in this one. So take X in A complement union B complement. A lot of times these will kind of follow similar paths, but not necessarily all the time. So because this is an OR, we're again going to have two cases here. So we say if X is in A complement, then that implies that X is not in A, which would of course imply that X is not in A intersect B, because it would need to be in A, which implies that X is in A intersect B complement. Okay, so we have a direct chain of implication here. We can do the exact same thing for if X is in B complement. Okay, that would imply that X is not in B, which would imply that X is not in A intersect B, which would imply that X is in A intersect B complement. And of course, if X is in both A complement and B complement, then you could just combine them and you get the same thing. So thus, we have A complement union B complement is contained in A intersect B complement. So overall, this tells us that A complement union B complement is equal to A intersect B complement. Okay, so we show both directions, and we typically will do that by taking one element from the first set and showing that it must then be in the second set, using these different definitions of complement and union and intersections and all that. Okay. So I'll probably put the other De Morgan's Law then as a homework problem, so you can try that one. There's also different ways you can do that. I mean, that's generally true with proofs, is that there's going to be a lot of different ways you can do these things. Like I know that a way this one is typically done is by contradiction. So, you know, in that case, you would take some X in this, and then you would say assume that it's not in this, right? Which I know is cut off here. So take an X in here and assume that it's not in the intersection complement, and then show that that leads to a contradiction. So that might be another way to, you know, try doing this one, but it's very similar to the logic we just used for this one. In general, I think that direct proofs are kind of preferred over contradiction proofs, if possible, but a lot of times the contradiction proofs are easier. They're both logically sound. It's just that direct proofs kind of tend to be more constructive, meaning that they give more insight into the problem. But it's not a hard rule.